Of course. Here is the clean voiceover script, containing only the words to be spoken, ready for a text-to-speech engine. Hello, and welcome to a deep dive into one of the most fundamental concepts in all of physics and electrical engineering, phase difference. Now, that might sound a little technical, but I promise you, the idea behind it is surprisingly simple and incredibly powerful. It's the secret language that describes everything from the electricity powering your home to the way sound waves combine to create music, and even how antennas transmit signals for your phone and Wi-Fi. By the end of this video, you won't just know the definition of phase difference, you'll understand it intuitively. We'll use this one diagram to unlock the entire concept, breaking down every single part, the waves, the equations, and those strange-looking arrows into simple, bite-sized pieces. So, let's get started. Let's begin with the most visual part, this graph on the left. What are we looking at here? This is a picture of two waves, which we'll call VA and VB. Think of these waves not just as lines on a screen, but as a story unfolding over time. The horizontal line, our x-axis, represents the forward march of time. The vertical line, our y-axis, represents some quantity that is changing, like voltage in a wire, the pressure of a sound wave, or the height of a water wave. First, let's follow the journey of wave VA. We'll call it our reference wave. Notice how it starts perfectly at the center, at the 0 point. As time moves to the right, it rises smoothly to a maximum point, what we call a peak. Then, it gracefully falls back down, passes through 0 again, and dips to a minimum point, called a trough. Finally, it comes back up to 0, completing one full cycle. This beautiful, repeating pattern is called a sine wave. Imagine a child on a swing. VA is like tracking the swing's position. It starts at the bottom, or 0, swings to its highest point forward, the peak, comes back through the bottom, swings to its highest point backward, the trough, and returns to the bottom again. That's one full cycle. Now, let's introduce our second wave, VB. At first glance, it looks very similar. It has the same smooth, sine wave shape. It reaches the same maximum height and the same minimum depth. But there's a critical difference. Its timing is off. Look closely at where each wave begins its upward journey from 0. Wave VB crosses that starting line before wave VA does. It reaches its peak before VA does. It completes its entire cycle before VA does. Going back to our swing analogy, it's as if there are two identical swings, but the child on swing B got to push a split second before the child on swing A. They are out of sync. This timing offset, this head start that wave VB has over wave VA, is the very essence of phase difference. We give this head start a name. In science, we label it with the Greek letter phi. On our graph, you can see phi marking the horizontal gap between the starting points of the two waves. It's a direct measurement of how much wave B is ahead of wave A in time. Because VB is ahead, we have a special term for it. We say that VB leads VA. If it were behind, we would say it lags. But here, B is the leader. Okay, we understand the visual. But how do we describe this relationship with the precision of mathematics? That's where these equations come in. Now, don't let them intimidate you. They are just a very condensed way of telling the exact same story we just saw. Let's break down the first equation for our reference wave, VA. It says VA equals Vm sine theta. VA is the instantaneous value. That just means it's the height, or value, of the wave at any single instant in time you choose to look. Vm stands for maximum voltage or amplitude. This is simply the highest value the wave can reach, the height of its peak. It's a measure of the wave's intensity. Sine is the sine function. This is the mathematical recipe that creates that perfect, smooth, repeating wave shape. You don't need to be a math whiz, just know that sine is the name of this specific curve. And finally, the Greek letter theta. This represents the phase angle. Think of it as a clock that tracks where we are within a single cycle. It starts at 0 degrees, goes to 90 degrees at the peak, 180 at the halfway point, and so on, all the way to 360 degrees to complete the cycle. As time moves forward, theta continuously increases. So, VA equals VM sine theta is a complete recipe to find the value of wave A at any point, take its maximum value, VM, and multiply it by the sine of its current position in the cycle, theta. Now for the star of our show, the equation for VB. It's VB equals VM sine of, in parentheses, theta plus phi. That plus phi is the mathematical way of writing has a head start. Let's think about it. For our reference wave VA, when its cycle starts, theta is 0. The sine of 0 is 0, so the wave starts at 0. But for wave VB, at that same exact moment, its angle is 0 plus phi. So we're calculating the sine of phi. Since phi is a positive angle representing that head start, the sine of phi is already a positive number. This is exactly why the VB wave on our graph starts above 0. This single plus phi elegantly captures the entire concept of leading. It tells us that whatever angle VA is at, VB is always at that angle plus an extra amount, phi. This confirms what we saw on the graph, VB leads VA by phi. Drawing detailed waves is great for understanding, but it can be slow and cluttered. So, engineers and physicists developed a brilliant shorthand to represent waves, the phasor diagram. It might look abstract, but it's a wonderfully simple tool. A phasor is basically a rotating arrow. That's it. It contains two key pieces of information about a wave. First, the length of the arrow tells you the wave's amplitude, RVM. Second, the direction the arrow is pointing tells you the wave's phase angle, its position in the cycle. Let's look at our diagram. We have an arrow labeled VA pointing straight to the right along the horizontal axis. This is our reference, our starting point. By convention, we place the reference phasor at an angle of 0 degrees. Now, look at the arrow for VB. It has the same length as VA, because we know both waves have the same maximum value. But its direction is different. It's angled upwards. The angle between VA and VB is labeled, once again, with our familiar phi. This diagram is showing us the phase difference directly as a geometric angle. So, how do we know which one is leading just by looking at the arrows? There's a simple, universal rule: the leading direction is counterclockwise. Imagine the phasors are frozen in a moment of time while they are rotating counterclockwise. The one that is further ahead in the rotation is the leading one. Since VB is counterclockwise from VA, it is the leading phasor. VB is literally ahead of VA in the standard direction of rotation. So, this simple diagram of two arrows tells us everything we need to know. VA and VB have the same magnitude, and VB leads VA by a phase angle of phi. You'll see the word radians here. Don't let that throw you. Radians are just another unit to measure angles, like using kilograms instead of pounds. A full circle is 360 degrees, which is equal to 2 pi radians. In advanced science and engineering, radians are often more convenient to work with. But the concept is exactly the same, it's just a number that quantifies that head start. So, let's take one final look and summarize our journey. We started with the waveform graph, which gave us the intuitive story of two waves, with one getting a head start in time. We then moved to the equations, which gave us the precise mathematical language to describe this head start, using a plus phi to signify a leading phase. And finally, we explored the phasor diagram, the engineer's elegant shortcut, which represents waves as arrows where the counterclockwise angle between them shows us exactly who is leading and by how much. 3 different representations, a picture, a formula, and a diagram, all telling the exact same story about the fundamental relationship between waves. Understanding this concept of phase difference is your key to unlocking the world of AC circuits, signal processing, and so much more. Thank you for joining me on this detailed exploration. I hope you now see the beauty and simplicity behind the concept of phase difference. Stay curious, and we'll see you in the next video.